In this video, we will talk about how to get the slope of a parametrized curve. So I want to do this with an example. Let's consider the parametrization x equals sine of 2t and y equals sine of 3t on the interval from 0 to 2 pi. The question is, what is the slope of the tangent line to the curve when t equals pi over 12? So first, I want to draw this in Desmos so we can visualize, well, what does this curve even look like? Ultimately, when we do our computation, it'll turn out knowing the picture won't be super important because we'll be able to derive a formula that works, even if we don't have the picture. But still, I think looking at this visually will help. Alright, so here is this curve in Desmos. I've already entered it in. I've already drawn it on the interval from 0 to 2 pi. And what this purple point here is it's corresponding to a point on the graph when I've entered it in as a equals 0, but that's just my t value. So I'm saying that's corresponding to when t is 0. And if you plug in 0 for the t, you get 0, 0. So it makes sense that that point is at the origin. But what if I change that a value and make it get a little bit bigger? So that means I'm changing the t to get bigger. As we do that, we start to traverse along the curve in this sort of direction. Okay, so let me bring it back to where 0 was. Okay, and now let's enter in our value that we care about, which is pi over 12. Okay, so that's where we are at pi over 12 on the graph. And I want to get that tangent line. So let's go back to our work. Alright, so to find the slope of the tangent line, we need a way to get the slope. So I'm going to talk about two ideas. So idea one is going to be similar to what we did in the last section when we had parametric equations. One idea was, well, we could try to eliminate one of the variables. Try to eliminate t, as we did in section 11.1. So for example, if I look at the equation x equals sine of 2t, and then we try to isolate for the t here and plug it into the equation for y, what's the issue when we do that? So the issue is we need an arcsine to do this. And arcsine is only defined when the angle inside the arcsine function is in between negative pi over 2 and positive pi over 2. That's when an arcsine is defined. But the problem that we run into in relation to that is because t is in between 0 and 2 pi, that means the angle 2t here, 2t is going to be in between 0 and 4 pi, and that lies outside of the interval on which the angle of arcsine is allowed to be. Okay, so that poses a problem. Alright. The other issue that we'll run into if we do that is, if you did try to isolate the t using this arcsine, simplifying it after you plug it into the equation for y is tricky. And that'll pose another issue with this. Okay, so what's another way we could do this? So idea 2 is going to be to use the chain rule. Alright, so when we use the chain rule, we're going to think of y as a function of x. Okay, so I could write y as being like y of x. I can write it in some sort of function notation. And let's think of x as a function of t. Okay, and when we do that, we get y equals y of, and we're thinking of x as being a function of t, so I'll write x of t. Okay, so I'm putting this all in parentheses. So now if we do the chain rule, and we take dy dt. So the chain rule says, we'll take the derivative of the outside function first, which is the y, but we'd have dy dx. And then you multiply that by the derivative of the inside function, which is dx dt. So that's what we'd get using the chain rule. So this is from the chain rule. And the thing that we want is dy dx. dy dx is the slope of the tangent line. So we can solve for dy dx by just dividing the dx dt over. And if we do that, we get dy dx equals dy dt divided by dx dt. And that's going to be true if the thing that we divided by, dx dt, as long as that is not equal to 0. And this is the formula for the slope of a tangent line when we have a parametrized curve. Okay, so that's why I've boxed this. All right, so now let's actually do this for our example. So in our example, if we want the slope, dy dx, we do dy dt over dx dt. Okay, so now we have to take those derivatives. So let's remind ourselves what were our original functions. This is where I got to zoom out a little bit, and zoom out a lot. Okay, so let's see. Y was sine of 3t, and then x was sine of 2t. So the derivative of y, zoom it in a little bit, would be 3 times cosine of 3t, and the derivative of x would be 2 times cosine of 2t. Sorry, I know that doesn't look super great just because it's harder to write when things are zoomed out, so let me zoom it back in now. Okay, so that's what dy dx is going to be. But we want to know what dy dx is at the point when t equals pi over 12. So now I get to plug that in, and we get 3 times cosine of, so 3 times pi over 12 is pi over 4, and then divided by 2 times cosine of, so 2 times pi over 12 is going to be pi over 6. All right, so let's continue to simplify. We get 3 cosine of pi over 4 is 1 over root 2, or we could also write it as root 2 over 2. And then on the denominator, we have 2 times cosine of pi over 6 is square root of 3 over 2. So on the top and the bottom, we could cancel these 2's and then be left with 3 root 2 over 2 root 3. All right, so in terms of our goals for this section, we have talked about how to find the slope of a tangent line to a parametrized curve. In the next video, we'll look at how we find the length of a parametrized curve.